OK, so today we're talking about parallelism and synchronization. From a parallelization perspective, we're worried here about parallel programming and how to build computer architectures that can run simultaneously multiple programs or multiple threads within one program. And today we're going to talk about some models of that, synchronization, and some primitives that help you solve it, like synchronization primitives and memory fences. This is a little bit of background and motivation for nowadays why we're going to multiple processors. So we're going to show here Moore's law plotted on a log plot, number of transistors going up exponentially. Our sequential performance has sort of gone up and then sort of stopped at this point. If you go look at the new Core i7 or something like that, it's kind of flattened out here. It isn't continuing to go up. And in fact, the numbers that they actually publish for sequential spec int are actually parallel numbers these days because they're using multiple cores to make spec int and spec FP go a little bit faster. And clock frequency has also flattened out. We didn't get to our 10 gigahertz processor. And largely that is due to us hitting some power challenges here, but it was also just incredibly hard to go design these very high frequency processors. So instead, we started to use these more and more transistors to implement multiple cores. So we started off with 2 cores and then 4 cores, and we've gone up from there. Intel, I think, is now selling an 8-core part, and their 10-core part's coming out soon. AMD has a 16-core part, but it's not a true 16-core part. I think it's 2 8-cores sort of glued together on a chip. And there's some other weirder stuff up here, some actual many cores, multi-core processors with more cores. But people did built multiprocessors before the multi-core revolution here. Back in these days, there were multi-processor systems. You could take multiple chips and put them together somehow into small systems or large systems. And for the rest of class, between now and the end of the term, we're going to be talking about parallel computing systems, both systems that have multiple cores on one chip and multiple chips in a system. And there's some subtle differences between the two of those things, but a lot of commonality. In today's lecture, we're going to focus on symmetric multiprocessors and memory systems for sharing of data and using shared memory to share data. But there are other ways to share data. And we're going to be touching on that in 2 lectures. We're going to be talking about messaging in more detail. I bring up symmetric multiprocessors because it's the simplest model to reason about. All processors are up here, and memory is down here. And let's assume there's no caches in the system to begin with. And everyone is equidistant from memory. And it's one big memory. You've multiple processors, which can either be running multiple threads in one program or multiple programs. A couple other interesting things is, these concurrency challenges don't come up just from having multiple processors. There are other things that can go and communicate with memory or communicate via memory. We have all these different I/O controllers down here, network cards, disk controllers, graphics cards, and they also want to read and write memory. So in your memory system, even on a uniprocessor system, there are multiple agents that want to read and write memory simultaneously. OK, so let's talk about synchronization. The dining philosopher problem is an example of a synchronization challenge. And we're going to talk about 2 major synchronization ideas, but there are more than are shown on this slide. Mainly the sort of broadcast models and other things like that. But for right now, when I say synchronization, it's some way to synchronize communication or arbitrate communication in a restricted fashion. So we're going to have two here. We're going to talk about producer-consumer. And that's the figure on the right here. A producer, as the name implies, produces some values, and the consumer consumes the values. This is the most basic form here, one producer, one consumer. You can think about having one producer, multiple consumers, or multiple producers, multiple consumers, or multiple producers, one consumer. A lot of this same ideas hold here. So that's one model that people like to use. Another model that people like to use, there's some shared resource, and you want to make sure that not more, let's say, than one processor is trying to access that shared resource. And this resource could either be a disk, a graphics card, or it could actually be a location in memory. And we're going to call this mutual exclusion. And the reason it's called mutual exclusion is it's exclusive who can access the resource at one time. Now, the generalized form of this, that's the most basic form, is only one processor or one entity can go and access the resource at a time. A more general form of it is some number of processors or resources can go access that at one time. And this is the more general semaphore question, which we'll be talking about a little bit later. So what I mean by that is you could have P processors, where let's say P is 20, and you could have a resource that no more than 2 processors can go access at the same time. You might say, well, why would you want to do that? Well, a good example is something like a network card that has 2 outbound queues, we'll say. So you can actually have multiple processors using it, but if you try to have 3 processors use that one network card at the same time, well, there's only 2 outbound queues, and it has to decide somehow to share those. So that's an example of a true semaphore versus just a mutex. OK, so let's go through some code examples here, because these are going to be instructive. And let's look at, actually, before I do that, you can even have, on a uniprocessor system, synchronization challenges. And how is that possible? Well, as I said, even in a uniprocessor system, you sometimes have multiple concurrent entities. So for instance, your disk drive doing a DMA into memory at the same time as a process is trying to read from that block, for instance. And you need to guarantee, for instance, that the disk block is completely read before the processor goes and tries to read the block. That's one way that this can happen in a uniprocessor system. Another way it can happen on a uniprocessor system is uniprocessor systems can many times be multi-programmed. So the operating system would actually time slice between different programs. And you'll get interleaving of instructions in a preemptive environment, at least, of different processes at the same time. So you might be running one process, the timer tick goes off, you stop that process, you switch to another process and start executing code from that. At some point, the timer tick goes off and you switch back to the first process. So even on a uniprocessor system, you can have synchronization challenges. OK, so let's look at a producer-consumer example. Let's look at in the abstract first. So we have a producer here, a consumer there. We're going to use memory and one big symmetric block of memory for all of the communication at this point. We have a queue between the producer and the consumer, shown here. And then we have a head and a tail pointer. So it's a FIFO. It says where the, or first in, first out queue. It's going to say where the head is, where the tail is. They can sort of move after each other. And let's say it's circular, so they wrap around at some point. You have a register value here on the producer, and you can move the tail pointer into this register. And then we have 3 registers over here, the tail pointer register, the head pointer register, and a register for the value we receive. And the reason I point out these different registers is just to show that the producer owns this register and the consumer owns these 3 registers. And as you can see here, this says rtail and that says rtail. So they're going to have different copies of rtail, and they could potentially get out of sync here. We're going to see some fun hijinks happening. OK, so let's look at a basic sequence of code here, where the producer wants to put an item X into the queue for the consumer to read sometime in the future. First thing it wants to do is it's going to read the tail pointer into its register. It's going to then, this is a load store architecture here. It's going to do a store of value X into the tail, which is going to put it here. Now we're going to have to bump the tail. We can't do this atomically, so we actually have to add 1 to it in our register space. So we just increment it in our own register. And then we're going to store this back into the pointer in memory. Seems simple enough. Let's look what the consumer does. Consumer loads the head. And the first thing it's really going to do here is it's going to try to figure out if the head equals the tail, because that will mean that the queue is empty and it just needs to block. Loads the tail pointer. So it loads the head pointer into this register, tail pointer in that register, and sees if they're equal. If they are equal, it's going to jump up here, reload the tail pointer into the tail to see if it got updated by this thread, and just spin here for forever until the tail pointer is not equal to the head pointer, which means there's some data available. And then we can fall through. And in the fall through case, we're going to load from the head into R, so into this register. So we did the read. And we're going to update the head pointer to the next location, save it off, and then do something on this value we got. So processes just do something. So this program's a little naive, because we've been talking about out-of-order processors. We've been talking about out-of-order memory systems. And in a perfect world, this is assuming that instructions are executed in order and that there's no interleaving between the consumer and the producer here, and vice versa in the memory system. So anyone think there's any problems with this? Problems? Does this just work fine? Yep. OK, so you're saying if the consumer runs before the producer does anything, you might just try to take values off the queue? Well, so let's guard against that and say the start case is head pointer equals tail pointer. So that won't happen. You'll sit spitting here. Now, because no one's like jumping up and screaming up and down at this point, you're sort of all assuming that these operations happen in order. But we've talked about out-of-order machines, which reorder loads relative to stores. We've talked about very interesting interleaving. We talked about out-of-order memory systems. So someone should be jumping up and down here and saying, what do we guarantee about loads and stores to different addresses? So we said, all we know is that a load and a store, or excuse me, a store and then a load that is serialized in that order on the same processor to the same address will happen in order. Our out-of-order superscalars and our out-of-order memory systems we talked about have defined nothing about ordering between processors or even memory operations inside of one processor. So that's what we're really going to be talking about today, is how to reorder those instructions and how to prevent that from causing havoc. OK, so let's look at this and let's number these purple instructions. So we're going to number store, and these two loads. And the reason we look at those in particular is this is basically updating state that this thread is reading from. And these are the two instructions that update that thread, and these are the two instructions that read that thread, or read that state, rather. So the programmer assumes that there's some level of causality here. Incorrectly. Producer is assuming, if you look at this code, that if this load happens after this store here, that there's some relation between 1 and 4. Namely, that 1 has happened by the time 4 happens. Not a good assumption in our memory systems, especially in our out-of-order memory system. Because if we recall, our out-of-order memory system said nothing about store ordering. The only thing we talked about was having a load to the same address as a store and not moving that load past that store. But otherwise, these two stores, our out-of-order processor can very easily reorder, and our out-of-order memory system can very easily reorder. Likewise, over here, these are just two loads. These loads could happen completely out of order in an out-of-order computer and out-of-order memory system. No guarantees there. So this assumption is bad in a multiprocessor system. Uniprocessor system might make sense. Multiprocessor system, bad assumption. So let's look at some sequences that are problematic. Namely, let's say 2 and then 3 happens, and then 4 and then 1 happens. So what happens when that? Well, 2 updated the tail. 3 reads the value of that new tail pointer. But at this point, we actually haven't stored the value into the queue because 1 never happened. We go execute 4, and it just reads garbage from memory. And then finally, the value gets updated. Totally valid in out-of-order memory systems that we talked about up to this point. Nothing wrong here. OK, let's say 4 and then 1 happen. So goes to load the head. Then the value gets written. And then 2 and then 3 happen. This is just completely out of order. Kind of no good semantics here. So this piece of code, which looks like it should have, the programmer would assume to have good semantics, basically has no useful semantics unless we define what those semantics are.